than zero. So, so first of all, a little bit about myself. As Dr. Nasser said, I'm a postdoctoral researcher at the University of Vasa here in Finland. And also I'm the acting master degree program manager currently in robotics. I got my PhD last year, 2024, from University of Vasa in computer science, and major is telecommunication engineering. And then back in time, like in 2013, when I graduated from Egypt, that was my hometown in Alexandria, from Alexandria University, in the same major in telecommunication engineering. Lately, alhamdulillah, we submitted a patent about positioning. We, together with Professor Muhammad al-Musrati here in Finland, we have developed a new method on navigation, and it was featured in many Finnish news here in Finland. Also, that allowed us to get the Innovation of the Year award in 2023 at our home university here because of this patent. And then I was selected in the 10 students, 10 young scientists in Finland to get recognition from the academy. Later, then we represented Finland in Singapore in the Global Young Scientist Summit, where we met some Nobel Prize winners in Singapore. And also we had a discussion with the Singaporean Prime Minister as well. And also later the same year, alhamdulillah, we got the EUNIS Innovation Cup in Spain of the same idea of the patent. So we competed with about 9 European universities and we won the first place. And then lastly, we got the Best Paper Award in America in a conference with NASA. So our paper also was the winner of the best paper in this conference. And some technical discussions in the media about this discovery. And also lately I was invited by the Euronews to comment on some of the GPS interference that happened in Europe, especially with the European Commission. Anyway, let's go back to our main topic for today, which is GPS, or we are going to learn later that it's not only about GPS, there are others as well. So GPS is actually, we're gonna go from the very, very basics until the very advanced stuff. So we start little by little to accumulate knowledge about GPS. So GPS is a global positioning system that actually maybe everybody use nowadays in their phones. You use GPS on daily basis. You can order an Uber or a ride, or you can order some food that comes to your doorstep with GPS. But how it works? First of all, we need to learn that GPS is not the only system. There are other systems as well. We're under the bigger umbrella of the GNSS. GNSS is the Global Navigation Satellite Systems. The GPS is just the American part of it. There is also the Russian part, which is GLONASS, Beidou in China, and Galileo in the European Union. There is also the Japanese QZSS and also the Indian IRNSS, or they're also now, they call it something else. We start usually using from smartphone when you open your location data, or like open the الموقع بالعربي. So in Arabic, the موقع or location, and then you can navigate your way from point A to point B. For example, the navigator will tell you to turn right after 300 meters, for example. Continue for 5 kilometers, turn left at 100 meters, go around the roundabout, and something like that. But the science behind it is quite complicated. We have many satellites in orbit, and then those satellites are sending their signals continuously on Earth so that every part of Earth can be covered. So you can even, while cycling, while driving, even the aeroplanes can use these such signals. And nowadays also we have the drones as well. So how it works, how it really works. Now we are going to go from basics to really advanced stuff. But first I would like to get like a very short glance how it worked before GPS or before we had satellites. Maybe the seniors here can know exactly what that means. In the pre-GPS era, or the time before 2000, that usually happens. Usually we used maps, and we used to ask people around. For example, you can ask, where is that street? Where is this avenue? Where is this building? And of course, it was very hectic, and it's very prone to errors as well. So we can talk about navigation and why we need to navigate. Actually, navigation actually helps us to go to our destination or reach destination. So destination requires navigation, and navigation requires positioning. So that's the very topic of our today's seminar. We're talking mainly about positioning that actually can leverage or give us navigation, and then navigation can help us to reach to our destination. So positioning is actually a little bit different than navigation. Positioning is to pinpoint where are you in this world or this map. So for example, you can position this building, that building, and you can say, for example, this building is close to the river, but this building is close to this landmark or something. So this is how positioning works. And we use, back in time, in traditional methods, we use something called compass or al-busla in Arabic. So we have to know our direction, north, east, west, south, and so on. Back in time, also, you could call someone and say, I'm lost, or I don't know I forgot the way home. I'm standing next to something. This is a way of positioning, actually. Or you can just look to the street labels. For example, where are you going? I choose this for you today since you are in Oman. I hope this is actually fitting. This I searched on Google to get some Oman lamp post and street post or street labels. But how it was in ancient time, like 1,000 years ago, the Arabs used to have the star constellation map, so to navigate through maps, and actually other nations as well, not only the Arabs. But the Arabs were among the first to use the maps of stars. And also we had this, once we had this invention, the astrolabe or astrolabe in Arabic, it's actually helped in finding the direction and headings. Or, for example, if someone navigates through the desert, usually there is the first guy in this convoy here is called a navigator or dalil, the one that leads the way. But let's go back to satellites, how they originate and why we need them. So satellites actually is anything that rotates around the Earth or revolve around the Earth. Whether the moon actually is our natural satellite. So the moon revolves around the Earth. And also there is the space station, and there are also small satellites. Anything revolve around the Earth can be called a satellite. So the moon is a natural one. The satellite are the artificial satellites. But what keeps a satellite into orbit? Why satellite doesn't fall? So satellites actually experience two kind of opposite forces. There is a centrifugal force, which is outwards, and the gravitational force inwards. So actually it's in the state of equilibrium due to the resultant of both forces. That keeps satellite in orbit. And of course, as you know, the space is vacuum. There is no media there. That also reduces the dragging forces. But we still have the gravitational forces, of course. So satellites are very useful in many applications, in military applications, civilian application, agriculture, even in healthcare and transportation. We need satellites all the way. The first satellite was around 1957 that was launched for communications, Sputnik, the Russian one. But nowadays we have the biggest satellite, which is the International Space Station. It's in orbit since 1990, and it's the biggest satellites ever so far. So it's like five football fields combined together. You can actually see some of their views from online if you would like to. And also you can still spot it in some of the clear skies, where I spotted some like a couple of times. You can see it actually from the coordinates. You can see when the station will cross your horizon. Then you can see it. I glimpsed it like a couple of times before. So the bands of satellites, they are actually divided with a distance from Earth. The first band is the low Earth orbit, or LEO. This is the closest to Earth. This is about 1,000 kilometers. And then the MEO, medium Earth orbit. This is about 20,000 to 30,000 kilometers from Earth's surface. And then the geostationary band, which is actually beyond 32,000 kilometers from Earth. It was called geostationary because actually any satellite in this band will revolve the same way as Earth revolves. So that's why it's geostationary. This is also like a map of the bands and also the speeds as well. So you can see the ISS, or the International Space Station, is around here. The Hubble telescope, the Iridium constellation, and there is the GPS and the Galileo and GLONASS and BeiDou. You would see that usually when satellites are closer to Earth, they revolve much faster, because that's how it works. Like if satellite is close to Earth, it needs to revolve very fast, not to be sucked by Earth, because Earth will pull it to its surface. But when you are away from Earth, satellite can have slower speeds. So GPS system. GPS actually started as a military application, but later it was released as an application for civilians. So it was started way ago, like 50 years ago, but we started to sense it as a civilian application in the early 90s. It's a constellation of satellites that revolve around Earth in the MEO band, and you can actually be seen. Usually it was designed in a way that you can be seen by a typical or average 7 satellites, 6 satellites, 8 satellites, and we would know more about that later, why we need to be seen by minimum of this number. In total, there are 32 satellites in orbit. And like this is the table of when and where they started to be launched. And they are actually renewing the constellation every 12 years. But what after launching satellite? Okay, we launched the satellite into orbit. What's then? So we have 3 segments of the system. We have the space segment, and we have the control segment, which is the ground controllers. And then we have the user segment, which is us, or the tablets or the smartphones or laptops that we use. So the control segment, that's actually control stations. So those are not monitored by us. It's monitored by the government of the USA, for example, in the case of GPS. And there are many control stations around the world. They scatter them everywhere. Even there is one still in the Gulf state here. There is in Europe and Asia and so on. This actually that feeds the satellites. But the satellite segment itself is actually being updated every 12 years. This is the lifespan of one satellite. So one satellite can be in orbit for 12 years. Otherwise, it will disintegrate and it will have defects. What happens to all satellites when we want to decommission one of those satellites? There is something called deorbiting or changing the course of satellites. So it's actually a controlled deorbiting. So satellite can change its course so that it fires up in the atmosphere and disintegrates. So it explodes in the atmosphere. But they do this in a controlled way so that it doesn't harm anybody. And the satellite can lay down in a point called Point Nemo. Point Nemo is the farthest point on Earth from any inhabitant. So it's the farthest from Europe, farthest from the South America, farthest from Australia, and so on. So all the space junk or space tombs are here. So this is like the cemetery of satellites. The positioning works like this. Let's have an example first. If we have such an equation, x minus 3 equals 0, of course, you know that the answer will be x equals 3, right? This one variable, one equation. But what if we have 2 variables and 1 equation? Can you solve this? Of course, it's mathematically cannot be solved because we don't have same amount of variables, the same amount of equations. So the rule is like that. If you have the number of equations should match the number of variables, then you have an exact solution. Or if you have number of equations more than number of variables, this becomes an optimization problem which needs a specific algorithm. This is the same way that happens in GPS. And in GPS, we can use 2D coordinate system like a planner, planar coordination, or 3D coordinate system, like in 3D XYZ. It depends on the application, of course. For example, for the drones, you can use 3D. This is the best because the drones need to know the height as well. So the 3D actually is the same as the 2D, but you are having an extra dimension, and also the resultant of 3 dimension is actually the position. And the Earth actually is also has its own coordinate system. You know the equator. This is the famous equator, and also there is a Greenwich meridian, or also there are other meridians as well. But in any case, we have coordinate system for the horizontal and the vertical one, and we can derive the XYZ from them, and that's actually how it works. So maybe we can wonder, if we want to make a 3D positioning, do we need 3 satellites or do we need 4? This question we're going to answer in few slides. We need first to know more about how GPS works before answering such a question. So satellite usually sends some very important information to us or to our receiver, that the receiver can demodulate and encrypt the data and know the position. So the satellite sends its own ID, its own orbital information, XYZ of the orbit itself, and the clock information about time. This is very important. So we have ID, orbital information, and time. And as we have seen this figure before, usually your phone can be seen by 6, 7, 8, 9, 10 satellites at one time. That's very, very useful, because then we have more than needed for 3D and 2D dimension. So the first satellite, for example, send its satellite ID, orbital information, clock information. The second will do the same, third, fourth, and fifth. All of this information coming to your phone at 1 nanosecond, could be, or millisecond, instantly. The signal received by the satellite is actually very complicated. You have the carrier L1 frequency, which is 1575.42 megahertz. This is a very typical frequency of GPS. This is called the L1 frequency. And actually it was modulated by chips with the same 1.023 megahertz. And actually this number actually can resemble the 23rd of October, which is the GNSS day. So on October 23rd, usually there is GNSS or GPS day, that celebration, because of this number. And this, of course, there is the navigation information coming inside this encryption, and it looks something like this out of phase. But your receiver will receive this through the front end antenna, and there is signal acquisition to acquire the signal L1 and actually remove the noise. The code tracking of satellite, because then you need to extract information from every satellite. And of course, the carrier tracking of the signal itself. Demodulation of the navigation data to know the clock, the time, and orbital information. And then the receiver will calculate satellite position first, satellite position in orbit. And then at the end, we have the receiver position, because then this is the very end result we need. That's why maybe when you open your GPS on your phone, your battery goes very fast, because actually it's a lot of computations, a lot of processing. So GPS is doing a lot of work. It's not just finding the map, it's about receiving from satellites as well. And by the way, all the phones, all GPS receiver, they only receive, they cannot send. So your phone doesn't send anything to satellite, it's just receiving. So if we talk in technical terms, so each satellite send X1, Y1, Z1, T1. This is the first satellite, and then X2, Y2, Z2, T2, and so forth and so on. So all this information is combined in your receiver. Then we have everything that we need. We make optimization using least square, for example, or Kalman filters, and then you find the position of the person or the user. So let's go back to our question again. Do we need 3 or 4 satellites? For 3D, we need 4, because we have time. Time doesn't show here in this dimension, but it's the fourth dimension and one of the very important dimensions that we use in navigation and positioning. So minimum of 4 satellites to have 3D positioning. But if you want to use 3 satellites, then you have 2D positioning. And then in the end, any driver can use satellite in such a way and can navigate its own way. It becomes simpler. Just on the side, maybe I will have a look on our invention, which is actually not involving GPS. It's involving another technology called LEO, or low Earth orbit satellites. I can show you how it works. Like we discussed already GPS, how it works, but this is something different, a little bit different. So we have LEO satellites, and they are sending MIMO beams or beamforming. And every beam has its own ID. And then through only the geometrical calculation of beams, we can have a positioning. No timing, no complications. There is no much hassle about the time and synchronization. And it's the same thing. Like this is the bigger beam is actually like this. This is the GPS. This is the GPS beam, but this is the beam forming of LEO satellites. And usually the GNSS or GPS beam is actually from far away, but the LEO satellites, you remember, it's closer to Earth. So it's actually more intense, it has more intensity. So it works like this. I hope, yeah, the video, yeah. So back in time, it used to be one beam, right? But or a LEO satellite or GNSS, but now it has beams or beam forming. So then if we have multiple satellites revolving around Earth with such a beam forming, it will show a very complicated pattern on Earth. So through the inclusion of beams on the Earth's surface, like it will have interlocked beams on the surface. By actually finding the intersection of beam, we can to some extent have a location of the user. And we have other algorithms as well to exclude the unresolved beam, unreceived beams as well. So through inclusion and exclusion, we can still have idea about the location of the user. That was in a nutshell the invention that we made with LEO satellites. So let's summarize the satellite things. You have a phone, you open your location service, okay? And then you are seen by such satellites. Those satellites send you, and you are receiving from them. And then you have the data coming from each satellite. Your receiver will resolve them, optimize them, until you have the location. Or let's talk from technical perspective. You have a phone, you are seen by satellite, you are receiving from them signal, carrier signal, pseudo-random codes, and navigation information, and out of phase or changed phase, modulated signal. And also you have your own receiver that demodulates everything, and signal acquiring first, acquisition, tracking, and then demodulation, and then satellite position calculation, and then in the end the receiver position or user. That's yourself. So that's for the part about positioning. The navigation then comes after the positioning. So it requires minimal algorithm. Like for example, going from this point to this point. If we know the position already, and this is the destination. Also, sorry, this is the destination. We are here. So going right, going left. This is actually another kind of optimization algorithm that comes afterwards, after the positioning is done. So positioning comes first, navigation comes next. And then this is how it works from satellite positioning perspective. Let's also summarize the other systems as well. Maybe we talked about this in the beginning, but also remember that we have other satellite systems as well, not only GPS. GPS back in time used to be called Navistar. Today we have Galileo, and I'm currently working with Galileo satellite signals. And nowadays we have some kind of research about that. And there is also the Russian GLONASS, the Peido or Chinese Peido, and the Japanese one. And there is also another Indian one, and there's coming up in a couple of years a Korean new satellite system as well. It will be called KPS. I hope that you have some questions. Please keep them keep them for now. We're going to answer this question afterwards at the end of this discussion. But first, let's talk about what happens indoors. We talked about outdoors and what happens outside, but what happens indoors? This is a very big question. Do you know why we don't? Sorry.
Dr. Mahmoud, maybe we have 10 to maximum 15 minutes, okay?
Yeah. So I will finish this. Yeah. Do you know why we don't use GPS indoors? Because it looks something like this. Like if you open your GPS indoors, you have a very big blue circle that actually doesn't give you much accuracy inside. Because we have an inherited problem that the GPS signal becomes weaker in indoors. And you know, there is also another problem of the null line of sight. Null line of sight actually when the signal is reflected, refracted, or blocked. So this is a line of sight, for example, loss signal, line of sight, but the red ones are line of sight. So actually it becomes a bigger problem when you are inside to receive such a signal. No GPS signal would work indoors to some extent. So that's why we needed indoor positioning system. That's not relying on satellites at all. An indoor positioning system, it's a real-time system that works or calculates the location of the user uniformly. Imagine you have, for example, a shopping mall or airports. You are inside such dense environment and you want to navigate your way. You want to go to this shop. You want to go to the WC, for example. You want to go to the kids area. You also can still navigate your way indoors. So we need different system for indoors. This is one of the experiments that we've done here at our university. You can see the level of accuracy here. It's centimeter level. We cannot use satellites anymore indoors. So we use instead another system. You can see in the corners here, there is our anchors, or it's a similar idea about satellite. We have 4 anchors at the corner of a room. So it gives us 3D resolution. Those anchors are actually radio frequency. And we're gonna talk about this in a minute. But in the end, it's the same idea. You have 4 or more anchors, and then you have the tag on yourself or on your phone, and you can start navigate around the room. It's in centimeter level accuracy. In this case, actually, I use something called ultra-wideband. We're gonna talk about this in a minute. So in IPS or indoor positioning, it's actually you can have 2 types. We can make a taxonomy of this. Building independent, like it doesn't matter the size of building or the shape of building, or building dependent. So the building independent, actually, there is some types of this system, and the other types in the building dependent one. I'm gonna talk about these ones that actually dedicated dedicated infrastructure is required. So you need infrastructure, you need anchors. For example, the ultra-wideband, the RFID, if you are familiar with the notion, ultrasonic Zigbee. And actually there are other systems that actually utilize the existing infrastructure like Wi-Fi, cellular one, and Bluetooth. Actually, ultra-wideband is one of the very prominent candidates. You can see from this graph here that this is like a 3D graph from the frequency perspective, the data rate, the spectral density. Ultra-wideband actually has less power, so it's very good with batteries. It has high data rate and also the bigger band. That's why it's looking big here. Wi-Fi, on the contrary, is actually less in resources than ultra-wideband, but it's more versatile on other levels. Bluetooth and of course GNSS is a different story. Usually for IPS or for any positioning system, we use metrics or to know is this a good system or not. We can use the accuracy, the availability, the coverage, the scalability, cost, the privacy, and of course robustness. Is it a delayed system or it's actually rapid or robust? The idea about positioning is the same as we talked in GPS case, but here we can talk more about it. You can use, like for example, several base stations, and we can use several algorithms or ranging techniques. In such a case, for example, we can use the angle of arrival. You can see the angle here in every case. So, and then you can find the position through angles. You can find the position through the radius of the level. Like for example, received signal strength. If you receive a certain amount of signal strength, you can deduce through the inverse square law what will be the distance from the receiver. And through the distance of the receiver, you can draw a circle or a radius, like a radius of this around the base station. And through the intersection of these 3 circles or 4 or more, you can deduce where is the user. This is actually the time. It applies to time of arrival, two-way ranging, the received signal strength. This angle of arrival, angle of departure, and here this is time difference of arrival. When the circle here is becoming here a hyperbola, not a regular circle. So again, we can use different algorithmic techniques like angle of arrival, time difference of arrival, received signal strengths, or mix of them. You can mix more than one technique together. And the technologies that are nowadays very popular, Bluetooth, the RFID, the Wi-Fi, which is very popular. Wi-Fi is the most popular one so far. And the inertial motion units, the infrared is less used, but then also the lasers are used heavily in very sophisticated applications in factories, or for example, in healthcare when they need millimeter precision and ultrasound and Zigbee. Ultra-wideband, in terms of accuracy, is the most accurate one. You can have 1 centimeter, 2 centimeter error with ultra-wideband. Of course, you can achieve more with others as well, but it's still ultra-wideband by far is the most accurate one. But as I said, it's a metric, I think. So ultra-wideband has good thing about accuracy, but maybe some bad things about other metrics. This is how it works to know the, like for example, in time of arrival. First, the tag. We have a tag and we have an anchor at the corner of the room. So the tag will start pulling and talk to the anchor. Then the anchor replies. This is actually through this first send and receive. This we can calculate the round trip time 1. And then again, there is another final message, so we can calculate the answer and the final. This is round trip 2. So you can calculate the time of flight 3 times. And as you know, the time of flight of a signal is actually, if it's known, you can know the distance, because velocity is distance over time. And we have actually c velocity here, or the speed of light. So if you know the speed of light, which is known, 3.8 times 10 power 8, 3 times 10 power 8, and then you know the time, then you can determine the distance. That's very basic rule. So time of flight, if it's calculated 3 times, we can have accurate estimation of the distance. So you have again a system, a user with a tag or a device, and they are in the anchors are in the corners, minimum 4 if for 3D positioning, the user tag, and there is this application that a real-time application that calculates it in real time, and we have a server to store this information. Of course, in indoors, it's much more problematic when it comes to barriers. You can have a wall, you can have some furniture, some desk, something on the wall, and some other structure that can absorb the signal. Of course, it's more problematic inside. So we still have the endless situation or non-line of sight. But of course, it has its own resolutions. We conducted a research about that, and we came up with 2 ideas to resolve this endless. Either using multi-sensor fusion, we can use multiple technologies at the same time, we call it multi-sensor, or we can use machine learning or learning algorithms. That's a way to resolve or mitigate the endless situation. Why we should use sensor fusion? Actually, if you know about the car, like the autonomous car or intelligent vehicle, nowadays it has cameras, it also have GNSS receivers, it has radars, and it has inertial navigation sensors. All are combined in one system. This is actually a kind of sensor fusion. Sensor fusion, when you mix many sources together, you have better accuracy and you have better redundancy, because you have the same information coming from different sources. That means the confidence is better as well and less errors. So the full integrity of the system rises up. So you have better resolution, better integrity. This is actually one of the benefits of sensor fusion. Of course, sensor fusion will add complexity to the system, but actually this can be solved as well. So again, let's study some basic stuff about sensor fusion. Why we use it? Because in ideal case, when you have one unique solution, like for example, you have one intersection point of all these lines together. But in reality, we don't have this ideal case. In reality, we have divergence. So actually, it's not one point, it's a set of points. So every one of these black dots or points are actually true. Any one you pick from here is good because actually all of them are lying in the intersection area, not a point anymore. So intersection area between all solutions. So that's why we need to use, this is actually over-determined system. We need to use we need to study fusion and use algorithm for this. We can actually make an analogy about such filter. So what is a filter in mathematics? If you want to make a cup of coffee, you put a boiled water, coffee beans, sugar, or milk, and then actually you have coffee, right? And then you dispose the grounds or the used grounds. It's similar here. We have a noisy measurements, we have initial guesses, we have the dynamic systems, and then we have estimations. It results in estimation, and then we remove the noises and uncertainty from the system. This is how mathematics works in sensor fusion. We conducted an experiment here at the University of Vasa in our laboratory called Technobotnia. You can see it's a very dense laboratory, a lot of robots, a lot of structure, a lot of metals, concrete, and so much stuff. This is what we call a dense environment. Dense environment is very challenging. But we had our system, we had a robot, autonomous robot. We had laser rangers to actually accurately map the distance in accurate measurements. And you can see we take one measurement 3 times, so we know that it's actually persistent. And we have the inertial motion sensors. This is actually my hand here. I was calibrating this sensor, and we have ultra-wideband anchors. We mapped the floor plan. We had a full floor plan of the area, calibrated the system, and calibrated the robots. And we put our stuff on it. You can see the ultra-wideband here. I hope you can see it. This is the white thingy here. And also we put the IMU down there. So this is the fusion-based indoor positioning system. We had a ultra-wideband system inside the robots, the Wi-Fi. Also, we added this Wi-Fi for comparison. We wanted to compare our ultra-wideband to Wi-Fi or Bluetooth and IMU, and then through some web server and node server, and then you can have the user location inside in the indoor. We planted here the anchors in several positions in this laboratory. It's a huge laboratory. We added our IMU sensor down there to know the headings and the velocity and so forth. You can see that it's there here, and the ultra-wideband up there. And this computer is actually the embedded system that we built. And this is how it looks from algorithmic perspective. We added some dead reckoning algorithm, fusion algorithm. It's Kalman filter, smoothers, linear regression. And in Wi-Fi case, we added more because Wi-Fi it has a lot of errors. So we added more algorithm to refine everything. And then at the end, we have estimated position. Of course, we use the robot data for training. This is how it looks on plan trajectory. So this is a robot trajectory here, and those are, you can see this ultra-wideband anchors. You can see these small things are anchors. We had a very nice result at the end, alhamdulillah. So we had this is the peak. This is a CDF of the system, and it is the best. It was the best, and actually it was resulting in 4.7 centimeter error in the mean absolute error. And of course, on the long-term error, it's about 10 centimeter or 9.6 centimeter. When we have 6 anchors, of course, adding more anchors is better. You can see from the results here. Summary, let's summarize everything about indoor positioning. You have an indoor environment. It's very dense, a lot of things inside, a lot of people. And then you choose the suitable IPS technology, whether it's a Wi-Fi, ultra-wideband, RFID, or Bluetooth, or anything else if you would. Study the end-loss situation, what will happen when the signal is blocked. And then decide on the ranging technique. Are you going to use the angle of arrival, angle of departure, time of arrival, time difference of arrival, or receive signal strength? There are many ways. And then decide as well, would you like to use sensor fusion or not? For example, you can use the inertial motion sensor, or like a gyroscope. This is a gyroscope, how it looks like. And in the end, you have a system that works in real time, in indoor. If you would like to know more, we have multiple publications about these matters for GPS, for LEO, for indoor, for ultra-wideband. Please, you can drop me a message. I can send you the publication. You can see that most of them are actually open access. You can actually visit them anytime. Thank you very much for listening. I wish you have had an enjoyable time listening to this lecture, and I would be happy to answer your question if you have any.
Thank you very much, Dr. Mahmoud, for this very interesting presentation. And I hope you are enjoying the weather there. It's minus 10 or 20 now in Gaza.
Yeah, we had now we had the sunrise now.
The sunrise is just started now.
Yeah, it's 10 a.m. in the morning, and
okay.
The sun started to rise.
Okay, yeah. Okay, so I hope if you have any questions, please, anyone has any question to ask, so please.
Yeah, someone raised a hand.
Ahmed?
I want to ask one question.
Ahmed?
What is better, visible light communication or ultra-wideband to use as a technique?
Oh, so this is Basma.
Hi, Basma.
Yes, she's asking about which one is better, ultra-wideband or
visible light. Yeah. Well, it depends again on the application, because every application will dictate or tells you what you need to use. For example, the visible light system, it might be good in some places where you don't have dense environment, like you don't have much furniture, many people are inside. But RF system or radio frequency system may be better because they can penetrate the walls and you have less problem with the null line of sight. So again, it depends. Are you using it in a? Would like centimeter level accuracy, or for example, you don't need centimeter level accuracy in airports? For example, if you are in an airport and they have designed a system for everybody to track everybody, it's better not to have centimeter level accuracy, because it doesn't matter if you are 3 meters away or 5 meters away. It's still the same. Okay, it will be still okay. But for example, if you are having these devices that works inside the human, you need millimeter accuracy. So you change the technology to have the same the desired result. So which one is better? We couldn't say unless we know the environment itself and the complication that matters inside.
Okay.
For example, if we want to test it inside the building, for example, inside the room, it's okay for use visible light communications, or it's better?
Yes, I would say visible light communication would be good. Ultra wideband is best. It's better when it comes to less people and then less density. Or I mean, if you are not actually covering a bigger area or larger area of land, ultra wideband is the best.
Okay, thank you, Doctor.
Thank you, Basma. Ahmed,
Hello, this is Ahmed. My question for the ultra-wideband solutions, what is the impact of having high density of signals, like jamming a lot of emitters at the same place, especially in the labs or the airport, where a lot of transmission from different bands? Is there any impact on the accuracy of the solution of the ultra-band?
Yes, that's a very good question. Actually, we had one of these problems before when we were working with ultra-wideband in our laboratory here. We were working in one of the labs, and the next to us were other colleagues working with 5G. So actually 5G was actually making interference with ultra-wideband, that it was very visible that the signal is affected by nearby communication. So there is a very big problem. This is actually one of the downsides and disadvantages of ultra-wideband, that it can be interfered with nearby signals easily, because it has a very wide bandwidth from 3.1 to 10.6, was it? Yeah, it's a very large bandwidth. So the 5G and anything that beyond 2.4 gigahertz can affect ultra-wideband. This is what we saw in the laboratory. It's a big problem, of course, but requires it can be mitigated using sensor fusion. You can add inertial motion unit to the signal. I mean to work with the signal so that they have less errors or mitigated errors.
Mm-hmm. So using IMU to compensate for this accuracy, does it help for a 3D, for example, like GPS positioning or for 3D positioning, or it will be applied only for 2D?
Yeah, it helps a lot. I can tell you this. When you add inertial motion units to anything, to GPS, to ultra-wideband, it helps a lot. It helps so much. But you need to pick up, yeah, this is very important as well. You need to pick up the best IMU sensor, because there are sensors in the market that are not the best. They are very sensitive to errors. So you need to pick up the right manufacturer, then it becomes very good. It actually improves the positioning accuracy.
So do you anticipate this one would be a good solution for the drone, navigation of a drone in indoor?
Yes, exactly. Actually, indoors they need initial motion units so badly. They are the most devices to need it, because they need to know the headings, they need to know the angles, the velocity, the acceleration, everything.
Thank you.
Yeah. So inertial motion units are very, very nice addition to complement and compensate the errors.
Thank you, Ahmed.
Thank you.
Is there any questions? So it seems that maybe we don't have more questions. I have just one question related to the scenario that you showed, that the robot moving around. So you said you have some anchors there inside the place. So do you have exact locations of these anchors to be used by the node, the robot, or you just place them anywhere in the
Yes, Dr. Nasser, that's a very good question. Yes, the anchors need to be placed at known positions, because those known positions will help us in making, for example, if we go back to the GPS case, we have the coordinates of Earth, we have the meridian, we have the equator. So we know the origin points. But in indoor positioning, we need to create our own system. So we need our origin point X and Y. So by placing these anchors in a known position, so we actually know the coordinates. That's easier for calculation. We cannot
make a reference. So you make a reference point, just any reference point you
yes.
So, but not the anchor points. They are not just related to the inside the building, not related to the real location, the real GPS location.
Yes, they need to be placed in a way to cover the whole area, and actually they need to be placed in location that they can see each other. Like the anchors need to have a line of sight with all other anchors.
Yes. But the reference location itself is not related to the actual GPS location of the anchor. The anchor is just a reference for the inside, the indoor positioning.
Exactly. Yes. Okay. That's true. Yes.
Okay, so we have more questions.
If you allow me to have another question, if nobody is interested to, what about this anchoring beacons? Can we have them mobile, and then they can do handover for a very complicated setup? Let's say that we place this anchor on a robotics platforms, and they can move, and there's like an ID number, and they can hand over to each other's, and the position can be compensated for. You know, if that's a good application for a very complicated environment.
Yeah, you mean that handing over to other robots?
Yes, exactly. So these beacons or these anchors is based on a platform where they are moving, and the position is calculated using IMU, for example, and they can hand over whenever there is offline position, or they are in the shadow area.
Okay.
And this is to resolve in a very complicated or a very dense areas like airports or factories or.
Okay. Maybe I haven't tried this before, but it could be like if you are having IMU, and IMU can still hold on the latest received position, and then it can actually compensate the errors until it actually regains signals again, if that you are saying.
Yeah.
Yes, that's possible.
I
This
think-
actually
I
what
think,
happens when you drive. When you drive, for example,
Mr. Mahmoud, I think if I interfere here, I think Ahmad's idea is that now you have fixed anchors, yes? I think Ahmad is meaning that anchors can be mobile. So
Yes, exactly.
They have a new, so
Can
you
be,
don't need to
sorry?
have mobile. So they can be moving, the anchors themselves, they become moving, and then they can cover areas which are not covered by the fixed anchors. I think this, Ahmad, what you are meaning.
Exactly.
Yes.
Okay. Yeah. But again, if you are going to move the anchors, which actually shouldn't be, but if you are going to move them around and making them mobile, again, you need to have some another layer of knowing where those anchors are, because you now move the anchors relative to what? You need to fix some points in the indoor environment to know your locations, because it's very important to fix the coordinates, to know where are you, because any indoor positioning system need to have its own coordinates. The Earth has, but indoor spaces is left to us to design its coordinates. So again, if you are going to move some of these, you need to fix others. You need to have some fixed anchors at least, so that you know where they are going and you track them.
Okay, thank you.
Yeah, and actually, one of these that, for example, when you are, this is what I'm going to say about compensating the error. When you are driving with GPS outside, and you go suddenly under a tunnel or a bridge, the signal is lost. It will say that GPS signal lost in your phone, but you still have position due to the IMU. The IMU is still working in the tunnel. That's
VR.
one of the advantages of the IMU.
Yeah, did reckoning.
Yes, dead reckoning, exactly. Yeah.
Okay, it's very interesting. Do you have more questions? Okay, so I think we come up to the end of this webinar session. Thank you very much, Dr. Mahmoud, for giving the time for this nice presentation, and I would like to thank all who attended, and wish inshallah in future we have more.
Thanks a lot. Thank you very much for having this seminar.
Thank you very much.
Thank you very much. Have a good day.
Okay.